Hello, everyone. Welcome to another LIC class. In the previous class, we went through some op-amp circuits. Specifically, we went through transducers. Transducer is a device that converts one form of energy to another. So it could be a current to voltage, voltage to current transducer. We went also through current amplifiers. We solved some practice problems. The last practice problem we saw was the inverting current amplifier. Today I'm going to continue the current amplifier, and let's hope we can finish this part. Do you have any questions from the previous class? No? Okay. So for the current amplifier, another type of a current amplifier, let me go back. I think we did inverting amplifier. Yes, let's go back a little bit. So the last amplifier that we solved the practice problem was a inverting current amplifier. So inverting current amplifier is an amplifier that amplifies the current, as it's mentioned, but it also inverts the current as well. This source of an inverting current amplifier must be a current source, and the output is a current that we get from the resistor. In a current amplifier, we must be careful not to saturate the op-amp, because if the op-amp voltage is saturated, the current would be also capped and saturated, and we won't get the current that we are looking for. There are some ways to overcome this issue, which I'm going to explain later today. But one limitation that we must always be careful of is the saturation voltage. The saturation voltage of an op-amp is usually a few volts below the supply rail voltage or the supply voltage. So if the supply voltage is like 15 or 16 volts, usually the saturation voltage is going to be 13 or 14 volts. And we solved this practice problem with a input resistor of 49, the feedback resistor of 1K, and the load resistor of 200K for 10K. So this one we solved with 33K, 1K, and 10K. Let's solve another one for 49K, 1K, and 200K. So the question is that we want to design an amplifier with a current gain of -50. The load is approximately 200K, assuming a typical op-amp I out max as 20 milliamps with positive -15 volts supplies. What is the maximum load current obtainable? So from the previous class, we learned that the current gain in an inverting current amplifier is equal to -1 plus Ri over Rf. The gain is -50, so Ri over Rf is going to be 50 minus 1, which gives us 49. So the ratio of the input resistor to the output resistor should be 49 to 1. We can have different possible combination of resistors. R1 could be 4.9K, RF could be 100 ohms, R1 could be 49K, RF could be 1K, RI could be 98, RF could be 2K, RI could be 24.5, and RF could be 500 ohms. So a lot of different combinations as long as we have the 49 to 1 ratio. But the problem is we can't go ahead and put any of these combinations because some of these combinations would create an issue. And the issue that we're going to have here, if we don't use the proper resistors, is that the output voltage and therefore the output current would go into saturation. So what we need to do, we need to find the saturating current. So we know that the supply voltage, rail voltage, for example, for this one is 50 volts. So the saturated voltage would be 1.5, 2 volts below that. Here we would assume that it will clip at 13.5 volts. So again, the supply voltage is 15 volts, but some of this voltage is consumed inside the op-amp, so the maximum output voltage that you can get in op-amp here is 13.5 volts. So the maximum voltage that we can have here is 13.5 volts. To find the maximum output current, we can simply use the Ohm's law and divide the 13.5 over 200K, which here gives us 67.5 microamps. Now, what we need to do is to figure out if any of these resistors create this current, and if we're going to exceed the output voltage in this system. One thing that significantly impacts the output current is this output resistor. So imagine instead of 200K, imagine we have one, let's say, imagine we have 13.5 ohms. So 13.5 volts over 13.5 ohms. This gives us 1 amp, okay? The maximum current that this op-amp could reach is 20 milliamps. So it's 50 times the maximum current that this could actually. Therefore, you're going to have a saturated current and you're not going to reach the full potential of the system. Is it clear? Yes.
Where's the 13.5 volts come from?
13.5, great question, by the way, again. Our supply voltage is 15 volts, okay? But some of this voltage is consumed inside the op-amp. So the maximum output voltage that an op-amp could reach is usually 1.5, 2 volts below the supply voltage rate. So 1.5, 2 volts is consumed inside. You can say and it's a voltage drop of the op-amp itself, and therefore the maximum voltage, output voltage that the op-amp could reach is usually 1.5, 2 volts below that, which here is 13.5. In exam or any questions, we usually provide you with that clipping voltage as well. You don't have to worry about that. But to be safe, you usually want to keep a threshold and keep a some difference between your maximum voltage and clipping voltage. You don't want your clipping voltage and the maximum voltage to be like if the saturation voltage is 13.5, you don't want your maximum voltage to be 13 volts. Maximum you want to get is like 10 volts. You want to keep a little distance between the maximum voltage and the saturating voltage. Okay, so do you want me to solve another one of these or one example? Okay, so imagine that we have the same inverting current amplifier. So we have a inverting current amplifier. This is positive, this is negative. And this is 16 volts, negative 16 volts. The maximum voltage that the system could reach is 14 volts before saturation. This is also ground, this is also ground. Input current is 1 milliamps. This is 20 ohms. This is 5 ohms. And we have two scenarios. First, in the first scenario, RL is 5K. In the second scenario, or let's make it 50K. RL is 50K. And Then we replace RL with 5 ohms. Okay. First of all, I want you to find the maximum current in the output, how much it could be for the 50K and the 5 ohm. And I also want you to find I out for both of them. What is the output current for both of them? And the equations that you need, the only equation that you need is AI is equal to negative R1 plus R1, RI plus over RF, or R1 over R2. Let me write it down here so AI is negative 1 plus First thing, what is the output current? I'm sorry,
Are you asking for IMAX or?
no, the I out, the output current. So what is AI? It's the output current ratio to the input current ratio, yes. And it's -1 plus Ri, which is 20, and Rf, which is 5. So AI would be equal to I out over In, which is 1 milliamps, and 5 over 20 over 5, 4 plus 1, 5, it's equal to -5. Therefore, I out would be -5 milliamps. For a typical op amp, this 5 milliamp is completely acceptable for a typical op amp like a 741. The maximum current could be 20 milliamps or so. So this is completely acceptable for the system. Now, let's see what the maximum current is when we have different resistors. So if we have a 550K resistor, IL would be equal to 14 over 50K, gives us 280 microamps, which is below this, completely acceptable. And this is below the -5 milliamp, the 5 milliamps that we had. And for the 5 ohms, IL would be 14 over 5, which gives us 2.8 amps, which is way above even the 20 milliamps that we have as in standard 741 maximum current. So as you could see, the resistor cannot be 5 ohm. If it's 5 ohm, it's going to go into saturation. Sometimes it's going to even damage the system that we have. But a 50K ohm is completely acceptable. Okay. So the maximum current that we're going to have here actually passing through that is going to 280 microamps for this particular case. Okay. So what does this mean? This means maybe some of you are getting confused. I see a little bit of confusion in some of the faces. So it means that this op amp is capable of delivering 5 milliamps, but the maximum that the load can take is 280 microamps when you have a 50 kilo ohm resistor. Does it make sense? It's like exactly you have an outlet. This outlet, the fuse is rated to 10 amps, so you can get 10 amps out of this outlet. But if you connect a charger to it, the load, because you have a high resistor load, the maximum current that you're taking from this outlet is 5 milliamps, for example, or 10 milliamps. Okay. So the load is, the source is capable of providing up to 5 milliamps, but the load, since we have a high resistor, the maximum current that is passing that, depending on the 14 volts, is going to be 280 microamps, which is in our safe zone. So if that goes to 2.8 amps, first of all, you can't deliver 2.58 amps. So maximum is 5 milliamps, and the system is going to quickly go into the saturation. Okay, so another type of amplifier that we have is called the adjustable inverter, non-inverter amplifier. So this is a very unique and interesting amplifier. This amplifier, the gain in this amplifier actually could go between a negative A and positive A. So for example, if the gain is 10, this amplifier, the gain can go from -10, which is an inverting amplifier, to positive 10. So the gain can swing between negative and positive. And the gain can also be 0 as well. So, and unlike the inverting amplifier, the positive is not connected to the ground. Therefore, the positive input or the non-inverting input would not be ground zero, virtual ground, you're gonna have a voltage which is calculated using voltage divider, and the voltage is the voltage of that, the resistor that is connected, which here it's a potentiometer. Therefore, you're not gonna have a virtual ground on the on the inverting side, or V negative as well. And this voltage, I'm gonna call it VA, is gonna be equal to VB, which is not zero. So the previous one was zero, this is not zero. So you're gonna have a little bit of boost in the voltage. So where do we use this amplifier? Can you think of an application for this amplifier? So one application, again, as I mentioned in the previous class, would be active noise canceling. So you get an input, you can create an exact output which has the opposite phase, or 180-degree phase, and it's going to cancel that out. So if I have two signals, I can give a signal to this. It's creating the inverting signal with the same thing. And if I add these two together, I'm going to have a zero. And if you want to tune down, you can, the noise canceling part, you can adjust the potentiometer to go from inverting to non-inverting, and then you can amplify it actually from zero to an inverting or non-inverting. So this is one application. Other applications is for phase shift, obviously. And when you have a gain of zero, means the output is zero, so it can completely cancel a signal as well. Imagine you using this as an audio amplifier. When you tune down change the potentiometer, the gain could potentially go to zero and completely eliminate the output and the volume on the output. There are a lot of applications for these. Communication systems is one application that we use a lot. In PWMs, we use this type as well. And actually, the gain is determined by a factor of K. And the way that the output is calculated is using this equation. So V out is equal to K Vn negative minus VR2. K could be between zero. K is between 0 and 1. And when K is 0, the gain is going to be equal to negative R2 over 1, or it's going to be an inverting amplifier, its maximum. And when K is equal to 1, AV is going to be R2 over R1, or its maximum non-inverting gain. So when K is equal to 0, it's an inverting, maximum inverting. So it's a max inverting. And when K is equal to 1, it's a max non-inverting. And when K is half or 0.5, the gain would be equal to 0. And how do we determine K? Using this equation. This is just the proof that I added here, but this is the main equation that we have. AV is equal to R2 over R1, 2K minus 1. And usually what we do is we set the gain to 1. You put an input and output, and we have the fixed resistors, and we can find the K. And if you find K, you can easily adjust R2 and R1 if you don't know K initially. But in most cases, we already know the K, we insert the K, and we find the voltage gain. Okay. Did you write this down? I'm gonna go and saw. write a practice problem. So for the first practice problem, imagine that for this inverting, non-inverting case, R1 is equal to 5K, R2 is equal to 35K. And R3 is equal to 1K. If Vn is equal to 5 millivolts, what is V out equal to? So R1 is 5K, R2 is 35K, R3 is 1K, and Vn is 5 millivolts. We want to find V out. Okay, this is pretty simple, just replacing this into what is it, V out? So using the equation, AV is equal to R2 over R1, so we didn't even need R3, that was just for distraction. Oh, I forgot to give you the K. Let's do it this way. I'm sorry, I forgot to mention the K. Let's say V out is 20 millivolts, or yeah, 20 millivolts. What is K? Or we can do it the other way around. We can say K is, for example, 6, and we want to find V out. So the only equation that you need is this equation here. Okay, what is K? Didn't get it.
0.79.
Like pretty close, I think. Yeah. So AV is equal to R2 over R1, 2K minus 1. AV, or the voltage gain, is the output voltage, which is 20, over the input voltage, which is 5. And R2 over R1, R2 is 35, R1 is 5. The units doesn't matter because it's going to be eliminated. Times 2K minus 1. So I don't know where to write it. 4 is equal to 7 times 2K minus 1. So 4 is equal to 14K minus 7, 11 would be equal to 14K, and K would be equal to 11 over 14, which is 0.79, yes? So K is 0.79. And sometimes it's the other way around. We give you the K and we want to find V out. Did you write it down? Can I go to the next one? Okay. So another type of op amp is called a single supply biasing op amp. This op amp is used when we don't have access to dual power supplies, like a outlet power supply, like a DC power supply. And we usually have just a battery. So one application would be when you have a single battery. Imagine you're gonna build an op amp amplifier with a single 9-volt battery. You don't have two batteries, or you don't have a dual power supply. We use the single supply biasing. And in the single supply biasing, one of the supply rails, the DC supply rails, is connected to the ground. And the other one, the single battery, actually both supplies the voltage, the supply of the op amp, and sometimes we use it as biasing for the input as well. So in this case, you may think because the DC voltage is connected connected between the supply and the input, it's going to create a unity gain, but it's not the case. Here, this is an AC amplifier, so the DC component is not going to have an effect on the system. So the DC gain may be unity, but here we are looking for AC gain, and the AC gain is important here. And we have a couple of coupling capacitors here, and the reason that we have these coupling capacitors is that we don't want this DC to interfere with our source. As we know, a AC current could pass, a AC voltage could pass the capacitor based on the capacitor size and its impedance, but the DC is going to be blocked with the capacitor, by the capacitor. So as mentioned, the coupling capacitor is used to oscillate the DC potential from the driving stage. The idea is to bias the input at 1/2 of the total supply potential. This can be done with a simple voltage divider. And this is used in a lot of systems that require a single battery to operate. For example, a small amount of analog circuitry may be used analog along with a predominantly digital circuit that runs off a unipolar supply. One example of this, and I've seen this a lot, is in these dusk to dawn sensors. They use them a lot. Motion sensors, fire alarms, a lot of those which have battery and you want to run. Sometimes we can't put multiple batteries, but we want to reduce the power consumption, so we use a single supply biasing. This is good for a switching system that you want to combine it with a digital system, logic gate, to be able to turn on and off a logic gate or some simple analog. But if you have a complicated analog signal that requires both the positive and negative cycles of it, this is not going to work well. So like, for example, a very good audio amplifier, it's not going to perform that well. This is another demonstration, the different type of a single supply biasing system. Here the positive is connected and supplied by the DC power supply. Again, one of the supply rails is connected to like a 9-volt battery, and the other one is connected to the ground. We have the DC the capacitors for coupling to isolate the DC and the AC. And we have an RF in the and RF in the feedback determines the gain in the system, and it's an inverting amplifier because the input is connected to the inverting input. So one problem that we had with current amplifiers is that current amplifiers have a limitation, and that limitation is because of the limitation that we have on the saturation voltage and current. To be able to address this, we use another circuit connected to the output of this current amplifier, which is called a current boosting circuit. The current boosting circuit is a class B or a class AB push-pull follower, what we call. It's comprised of 2 diodes and 2 transistors. One of them, you can see it's an NPN, the other one is a PNP. So we have an NPN and we have a PNP transistor. And you can see that one of them is, the reason that we call it the pull-push is one of them actually pulling the current and the other one is pushing the current. That's the reason we call it pull-push current amplifier. And what this technically does is that you're cascading technically 2 amplifiers. One of them is an op amp, the other stage is the pull-push. We can build this with MOSFET transistors as well. And the good thing about this is it's actually basically like a switch, and you would have almost no limit on the output current. You can produce large output currents. The op amp here technically acts like the base controller for the transistors and controls the switching and the forward and the reverse bias of the diodes as well. So sometimes to increase the system linearity, we can put this inside the op amp's feedback as well. And the other thing that I want to mention is we can see that here the input is connected to the non-inverting input of the op amp. And when we have a non-inverting op amp, the output and the input would be in phase, so we won't have any feedback issues as well. Because the transistors are going to create a little bit of delay. If we have an inverting amplifier, that's going to cause a little bit of problem. But since this is a non-inverting, it's going to be no problem in the feedback and maintaining the correct feedback in the system. When I mean high current, doesn't mean you can create like a 2000 amp or something. Obviously, all these electronic transistors and diodes and op amps, they have limitations, but it won't go into saturation like an op amp. You can create higher currents out of this. And the main function of these is when we usually have a small resistor in the output and a small load. So for example, if I have a load which is short-circuited or a very low resistor, these low resistors, as you know, according to the Ohm's law, I is equal to VR. V is fixed. If we reduce the resistor, the current is going to increase. So if we have a short circuit, the current is going to be maxed out. Okay. So in some applications, we have low resistors. And one application of a low resistor is in your headphones, like an AirPod or any type of speaker. Those speakers, I don't know if you've seen a speaker inside a speaker, usually the resistors are in the range of ohms. A normal speaker is like 8 ohm, 4 ohm, 10 ohm, something like that. And the op amp is designed for, as you saw from the previous slide, when we added, and that's was actually the reason, one reason that I added this 5 ohm here, to see that adding a 5 ohm would increase our current to 2.8, which is over our limit. And a normal speaker has a 5 ohm or 8 ohm resistor, so it's gonna put our system definitely into a saturation. An op-amp current amplifier is designed for a resistor that is usually a load resistor, which is usually over 1K, okay? So R out for an op-amp should be usually over 1K. Anything below 1K, it's gonna create problems. It's gonna put our current into saturation mode. So definitely when you have an RF, which is 5 ohms, it's going to definitely put your op-amp into saturation. To fix this problem, as mentioned, is to use this current boosting technique. So one application for this would be anything that has a speaker is going to be one application of this. Because speakers usually have the maximum of like a few ohms, like 2-3 ohms to maximum of 20-30 ohms. Do you know why the speaker resistance is so low? Does anyone know how a speaker works? Yes, perfect. So a speaker, we usually have a permanent magnet. I'm going to draw it with the black one. And we have that right. There's a flexible, I can say, part in the front, which is connected, and inside the permanent magnet, we have a gap, a small gap. So if we look it from the top, you have a small gap in that magnet. Inside that magnet, you're gonna have this wire coils going. So the wire coils is actually connected to the speaker itself. Imagine we have these wire coils. And what happens is, since we have a permanent magnet, we have the N and S in the permanent magnet. When you pass a current through this, according to the Lenz's law, you're going to create a magnetic field. You remember the right-hand law? Did you have a right-hand law in the physics? So the direction of the current, if it's your thumb, your fingers is going to show you the direction of the magnetic field. So if the current is going this way, you're going to have a magnetic field, which is, for example, going inside. And from this part, it's, for example, going outside, something like that. So you're going to create an N and S inside that coil as well. And when they are opposite, they are going to attract each other. When you have the same N and S, you're going to actually repel each other. So if I have a current that it's like this, it's going to constantly change the magnetic field direction, and you have this coil is actually connected to the flexible part of the speaker, and the magnetic field is gonna have a movement, and you're gonna hear the movement is gonna move the air, and you're gonna hear a sound. So you may ask why speakers have high resistors, because to have a good speaker, you need to create a very good magnetic field, and to create that magnetic field, you need a very good conductor. So usually we just use a coil of copper wiring, and that copper wiring has a very low resistor. It's sometimes close to even 0 if you have a very good copper wiring. So the resistor here is around 5 to 20 ohms or something like that. And there's nothing you can do about it. You have very low resistance. That's the reason the most sensitive part in usually a headphone is the speaker, the end speaker itself. If you put too much current, it's going to immediately burn this coil, and then you're not going to hear anything. Or sometimes if the coil doesn't burn, that's going to rip off. You would have a punch in the system, and it's not going to create a good sound. Okay, so in those situations, you need a current boosting system. We also have, I'm going to quickly go through these other type of amplifiers. One amplifier is a log amplifier, log amplifier, instead of having a resistor in its feedback, has a transistor. This amplifier, the output voltage is K times the natural log of the input voltage. And this is equation V out is KLN. Vn over V reference. And V reference is the normalization constant in volts, and K is the scale factor. We can build the log amplifier in different ways. This is another log amplifier with saturated current and temperature compensation system. Again, temperature compensation could be used, for example, in an ultrasonic distance measurement system, or we can use it in audio amplifier, different applications. I'm just going to touch base on the log amplifier. We're not going to have questions on this. This is just for you to know we have a different amplifier called a log amplifier. And we use it in digital design systems and power electronics as well. This is another log amplifier with saturated current and temperature compensation using 2 op amps. A simpler version, V out compensation would be 1 plus R2 over RTC KT over Q ln of VI over V reference. Again, this is used in a lot of these switching amplifiers, different sensors. If you want to build, again, a infrared heat sensor, this is a good amplifier for that as well. I think we are out of time, and also the lecture, this part is done. And thank you so much. Oh, by the way, the lab manual is online. I haven't made it available yet because I didn't get the parts that we need for today's lab. For the online student, I will post the lab manual. They have to do it in a different way using simulation and some videos and links and an instruction on how they should do the labs. For the online students should do the labs. Okay, thank you so much, and I will see you next week. I will